All right, so let's talk a little bit more about light. So yesterday we kind of introduced the idea of what is light, how is light created, the fact that light moves as a wave, as also as a photon, which is a little packet of energy. And so we're going to continue on with that theme of the fact that light or electromagnetic radiation can move as a wave or as a packet of energy. And remember how light is created? It's by the fact that when an electron is at an excited state or farther away from the nucleus and falls back down at the different steps, it releases energy in the form of light. So if you have the opposite end of that, you can kind of take light and make the electron bounce off. This is also known as the photoelectric effect. So it's kind of the opposite of how light is created. You can actually take light from the sun or some other source and make electrons shoot off. So photoelectric effect is how solar panels work. Basically, they achieve the ionization energy, which is the energy required to remove an electron, like the sun, light from the sun from a solar panel. So it's the opposite of how light is created. Light is created when electrons fall from an excited state to the ground state or down back to the nucleus, closer to the nucleus. And the opposite would be light makes an electron bounce all the way off of an atom or nucleus. And that's how the movement of electrons is electricity. So that's just a side note, but going back to the idea that light can travel as a wave or as a photon. So light travels in little bundles of energy called photons. And guess what? We've got a couple equations for us today. One of them is Einstein's equals mc squared. So what does E stand for? Energy. M, mass. C is actually the speed of light. And how fast does light travel? Well, if you could put light around the world, it would travel around the world 7.5 times with a speed of 3.00 times 10 to the 8th meters per second, which is also 300,000 meters per second, which is also 186,000 miles a second. So to go around the world 7.5 times, light moves relatively quickly, but it does have a finite speed. So that's just something I want you guys to be familiar with is, energy from light can be equal to the mass times the speed of light, and speed of light is going to be key here for us. So a couple more equations that we're going to be using more often than E equals mc squared is this. So C, remember, is the speed of light, equals that weird upside down y, which is also known as lambda, and then this what looks like a v, but is actually the Greek letter nu. So C is the speed of light. That lambda is the wavelength, so in essence how far it is from one wave to the next. So if you're going back to this picture here, this would be right there, that would be a wavelength from the top to the top, or from the bottom to the bottom, or from the middle to the middle. That is a wavelength. Times the wavelength times nu, which is known as frequency. Frequency, the units for it are hertz, or 1/2 so it's like waves per second. So speed of light equals wavelength times frequency. Another equation I want you guys to be familiar with is this. We have E, maybe you think it's energy, equals H times that nu or V looking letter. That is once again frequency, but energy is E in joules. And what is a joule? It's not a vape, it's actually a unit of energy. It's basically how much energy it takes to move a 1 kilogram object with a 1 Newton of force for 1 meter. So that means a lot to us all, but that's just what the energy source is measured in. H is actually a constant value, but we'll go back to nu as frequency once again. And then H is this Planck's constant, 6.626 times 10 to the negative 34 joules per second. So making sure we remember how to use our exponents on the calculator. So let's just do a couple of questions. First one says a quantum of light, so basically just some energy of light, has a wavelength of 6.00 times 10 to the negative 7th meters, which is also known as 600 nanometers. So 600 nanometers is something that's visible to the naked eye. It's one of the types of visible light that we have. And that 600 nanometers is going to be like an orange color. So if we're looking at this is orange light. What is the frequency of this quantum? So some things to be aware of is I have frequency, I have wavelength. So which equation has frequency and wavelength? That's it. C equals wavelength times frequency. So I have my wavelength there. I'm going to plug this in. c, the speed of light, equals wavelength times frequency, or the way lambda times nu. 3.00 times 10 to the 8th meters per second equals the wavelength, 6.00 times 10 to the negative 7th meters times nu, or the frequency. Divide both sides by 6.00 times 10 to the negative 7th. I ended up getting that the frequency is 5.00 times 10 to the 14th per second, or hertz. So in essence, what this is saying, the frequency is how often something happens. And so you're having these waves occur 5.00 times 10 to the 14th times per second, or waves per second. So really lots of waves, and that is dependent upon its wavelength. So if I was to take this information, then I can look at how much energy does this wavelength have, or how much energy does this quantum of light have. So I can take the Planck's constant, I can take the frequency, which we just figured out on the previous question, and determine how much energy this light has. So energy is equal to Planck's constant, 6.626 times 10 to the negative 34th joules per second, times 5.00 times 10 to the 14th waves per second, or hertz. Seconds cancel out, and my answer for energy is going to be 3.31 times 10 to the negative 19th joules. So just to kind of give you guys an idea of a couple of light equations that we're utilizing. So we got to apply our knowledge about electrons falling and giving off light, and then taking a look at what kind of frequency, wavelength, and energy those quantum of light have. So they're all different depending on how far those electrons fall, and that's just kind of something I want you guys to be familiar with. All right, hopefully that was helpful.